So this next topic is called kinetics, and it refers to the rates of a chemical reaction. You have some reactions that go fast, and you have some reactions that go slow, okay? So, for example, a fast reaction would be a bomb, okay? An explosion. A chemical reaction that produces products very, very quickly. Okay? I could also have a slow reaction. And a slow reaction might be something like, a rusting car in my front yard or something. Rusting is a slow reaction. Now, in terms of energy change, these might be very similar. The only difference is the bomb releases its energy super fast, and a rusting car releases its energy really, really slowly. So basically, the way we measure kinetics, we're going to keep it pretty simple, but the rate of a reaction, okay, how fast it's going to happen, is going to be equal to a change, that delta, a change in the concentration per change in time. So it's really sort of similar to, when you measure how fast you're going in a car, it's miles per hour. Here it's concentration per time. Now, to really handle this properly, you're changing two variables at once, and that's the whole idea of calculus. And we would need calculus to solve these mathematically, but we're not going to really worry about that very much. We're going to kind of stay on the conceptual side of rates of reactions. So, all right. So there's a diagram that's really important in chemistry, and it looks like this. Maybe I'm going to change the x-axis a little and just call it time. Sometimes it's called reaction coordinate, but I'm going to call that time. And over here I'm going to call the y potential energy. Okay, so potential, and that's stored energy. And or chemical energy. And if you remember back to I forget what chapter, but delta H is sort of what we're talking about here. Okay, so I have potential, energy, delta H versus time. And if I track a reaction, many times it's sort of drawn this way. Reaction, and I get a graph that looks like that. And let's say at this point, okay, I have these two reactants, A plus B. So at this point, right around here, all right, I have a molecule A, okay, speeding along, and I have another molecule B speeding towards it. Okay. Now, part of the collision theory that I'm talking about, or rates of reaction, is that A and B have to hit each other in order for a reaction to happen. And because they have to hit each other, okay, that alone is going to introduce a little bit of a time factor. But according to this graph that I'm drawing, okay, that's what's taking place along here. A and B are speeding together. Now, this part of the graph going up here to about that point right there, well, that's the point at which A and B have smacked together. So now I have A and B. They've hit each other. There's an impact. They're getting ready to possibly react. So this is sort of step one right here. Okay. Then step two is here where they're going to start smacking together. Well, this is called an activated complex because it's really an unstable critter. So it's an activated complex. And what it means is it's the moment at which the two reactants have hit each other. And two things can happen, all right, at that point. Either the collision is successful, and I now end up with this new product C that goes speeding off in its direction somewhere, or for some reason the collision wasn't, vigorous enough, I guess. So A recoils off, goes its merry way, and B goes its merry way as if nothing happened. So I'm kind of right back down here on this line. So the activated complex is at the top of this peak. Okay? And for some reason I can't get that to draw. So, but anyway, that's the activated complex right there. Chink, chink. Okay, it can go two ways. Now, if C is produced, okay, that means I've not gone down this hill, and I have this product C right there. Well, the factors that determine how A and B go together are going to affect the rate of this reaction. One of the factors is the kinetic energy of A and B. How fast is A traveling and how fast is B traveling? So if I heat up A and B, chances are they're going to hit each other with more energy, giving the rate of the reaction, or the possibility of C being produced, that much greater. Okay, so temperature is a factor, big factor. We'll talk about that. The higher the temperature, the higher the kinetic energy, the faster the rate of a reaction. Now I could also ensure that I get more collisions if I have a greater number of A and B's. Okay, so if I increase the amounts of A and B, so now I've got a whole bunch of A's speeding towards each other and a whole bunch of B's speeding towards each other, chances of a good collision are greater than they were when the concentrations were low. So concentration is going to be a factor. Okay, so that's the second factor. Now if they're gases, pressure is going to be a factor. But that's only for gases, because again, pressure is proportional to moles, pressure is proportional to temperature, the whole darn thing from the gas laws. If I increase the pressure, I'm going to have more effective collisions. Now, the last thing, I've changed temperature, concentration, and pressure. The last thing is an addition of a catalyst. And what a catalyst does is it drops the height of this hill, okay? And this hill right here, right there, that distance, that amount, the amount of energy that it takes for this collision right here to happen, okay, that hill is called the activation energy. And that's going to be a characteristic of the reaction. Some reactions require a great deal of activation energy, others don't. It's just the way it is. Okay. A lot of times, if I have a candle that I want to start burning, I have all the oxygen I need. I have all the carbon I need in the candle. What I'm lacking is the activation energy, and that activation energy is the spark or the light that I get things rolling. Other reactions just happen because they happen to be at enough energy for this to happen. So anyway, what a catalyst does is it lowers the activation energy, thereby making this hill not as great. I'm then going to have more effective collisions, and everything is going to increase that way. All right? So this brings up one little factor that'll kind of tie into the next chapter, or the next section of this chapter, is if A and B can go together, okay, and if, provided they have enough activation energy to get over the hill, to come down and form product C, might there be times when C's can go back over and form A and B? And that's sort of the topic of the next section that we'll talk about.